Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our structural analysis and design software R section in RFEM. The topic for today's presentation is custom cross-section modeling in R section 1. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Cho will be your moderators, answering any questions you may have. They are both technical support engineers, also located in our Philadelphia office. We always want to encourage everyone to ask questions throughout this presentation. You can do so within the GoToWebinar dialog box as shown here. We'll do our best to get to all your questions, but if by chance we don't, we'll certainly send you a follow-up email afterwards. So I'll quickly go through the content that we will cover over the next hour today. I will begin with a brief introduction to our standalone program R section and the analysis methods available. We'll then move on to several examples today, starting first with a built-up hot-rolled steel section. Our second example will be a cold form steel shape where we will import in a DXF file. Example 3 will be an aluminum extrusion. This will be a little bit more of a complex section, also importing in a DXF file. Example 4 will be an additional aluminum extrusion. And finally, we'll move on to our fifth example, which will be a reinforced concrete massive section, similar to the one that you see over here on the right-hand side. So ultimately, after we calculate the cross-section values of these custom sections, we want to integrate them into our FEA program RFEM 6 for the full member analysis and design. So we'll see a quick example at the end for this. So moving on to the analysis options available within this standalone program R section. We have either the thin-walled analysis or the finite element analysis available as the two different methods when you do create a new file. So thin-walled analysis should be used for sections with exactly that. They have thin-walled elements. These can be open, closed, or even connected cross-sections. In turn, finite element analysis methods should be used for sections with massive profiles. And these massive profiles can also include openings if we wanted to consider that with the cross-section properties. Now, for some of the section properties that will be calculated, despite which analysis method that we choose, these will be identical. And the reason why is because we're going to reference what we call the part to calculate properties such as the area, the moment of inertia, the radius of gyration, section modulus, and many more. So again, it won't matter which analysis method you choose, that some of these properties will remain the same. However, there are a set of other properties that will vary depending on which analysis type we choose. And in particular, this is going to include shear area, torsional constant, warping constant. So on our next slide here, let us dive a little bit further into the thin-walled analysis. So again, we want to really apply this analysis type to those thin-walled cross-sections. This would refer to aluminum, to steel, cold form steel, and there's a couple examples shown here on the right-hand side. Now, in addition to generating what we call the part, we are also required to generate what we call the elements. And this will make more sense as we get into our example models today. But with these elements, we are going to apply simplified assumptions and analytical formulas. The stress and force flow is considered along these simplified elements' lengths, but not their widths. So topics like the shear, torsional, and warping properties are going to reference those elements only. So we're not able to take into consideration the full cross-section geometry here. For example, we're going to simplify and maybe exclude the fillet radius for some of these cross-sections. Now, this next point I really wanted to emphasize, and the reason why is because when we generate these elements with this thin-walled analysis, and we bring it into RFEM for the full analysis and design, we are able to carry out the local buckling checks of these custom cross-sections according to the ADM standard, the AISI, the CSA standards, and this is something that is very unique to our section in comparison to a lot of other competitor programs to calculate cross-section properties. Again, we can take it this step further to carry out the local buckling. Now, with the thin-walled analysis, there may be limitations. So if we have very complex sections or sections that deviate greatly in the shape from what we call these generated elements, then we may be incorrectly calculating the properties for shear, torsional, and warping. In this case, we would want to move forward with the FEA method. So on this following slide, we will go more in depth to the alternative analysis type, the finite element analysis. Now, this should always be used for massive cross sections. So when we're talking about concrete or timber, again, a couple of examples shown over here on the right-hand side. The finite element calculation method will be applied. This does require, like any finite element analysis, that the adequate mesh be created for adequate results. But our section will do all of this automatically for each cross section, so we don't necessarily need to manually mesh any of the sections. Now, this does require a higher numerical and time demand when we compare it to the thin-walled analysis with analytical calculations. But I think you'll see today that it's really negligible when we're talking about just a simple cross-section calculation. The finite element analysis offers a wider range of applications, including for complex sections. So we see this section down here in the lower right-hand corner. This is an aluminum extrusion that we would probably prefer the thin-walled analysis, but when we're getting into such complex shapes, we really would want to apply the finite element analysis here. And this will be one of our examples that we cover today. The stress and force flow is considered along the entire cross-section length and width. Also, those shear, torsional, and warping properties, we're going to reference the part rather than those elements from the full cross-section. But it is possible to still generate these elements with a finite element analysis method. It's just not required. So if we are wanting to carry out local buckling checks, but we're carrying out a finite element analysis, again, this is possible by generating these elements. We can bring them into RFEM and still get those local buckling checks according to the standards. And again, these examples today will kind of cover all of these different scenarios. So let us begin in our section here, where when we go to create a new model, we would give it a model name. And as mentioned in the PowerPoint, we would want to choose the analysis method. So for this first example, this will be a built-up hot-rolled steel section that we will carry out according to the thin-walled analysis. So once we have input in this information, for those of you that are familiar with our other program, RFEM 6, the interface looks almost identical. We have our navigator to use over on the left. We have some tools up here at the top, as well as some modeling tools down at the bottom. And then we have our table to work with as well. Here at the graphical interface, we'll begin to create our cross-section. So I'm going to right click over in the navigator to create a new section. And what we have here is the ability to access our cross-section library. So all the standardized sections from the various standards are going to be included in here, as well as some parametric sections. We want to begin by accessing a W shape, and over on the left we're going to use our filters to set this to the United States. We also set this to the AISC 16. We choose the W shapes here, and then we will scroll down to choose a W30 by 90. Sorry, I'm going to choose a 30 by 99. Now we do want to assign here the material to the cross-section. So very similar to the cross-section library, we're going to access our material library. Again, utilizing the filters on the left, we're going to choose steel, and then we can select the AISC 360, the latest 2022 standard. And here is where we can go ahead and choose the A992 material. So now this material is assigned to this cross section. So once we have defined this particular section, we can actually choose a point here at where we would like to insert it within our model. So I'm going to take this top point and select it. It's going to be automatically inserted here at the origin. I click OK. And now we see this standard W shape shown here. Now we do want to add a channel cap to this. So I'm going to once again right click to create a new section. We do have some quick sections we can access along over here on the right where I can choose a channel section. Once again, setting my filters to the United States, I'm going to choose the AISC. And then for my channel section, we will choose a 15 by 33.9. We do want to assign a new material to it. So we're going to access our material library. And this time we will choose a 36 material to assign to this particular cross section. We click OK. Now we want to rotate the cross section 90 degrees. And again, I'm going to select a point here where I would like to insert in the model, not necessarily at the origin, but this time I'm just going to zoom in here and choose a point above the W shape. So when I click OK, we clearly need to move this cross section down to the top of the flange. So we can easily do this by highlighting the cross section entirely using our Move Copy tool. And I can graphically select my displacement vector by choosing 2 points. So I'll select here the point at the bottom of the channel, and then at the top of the flange will be my second click. But I don't want to move this in the Y displacement direction, so we'll go ahead and set this back to 0. We're only going to move it vertically in the Z direction. And now we can see that these two cross sections align well for our built up section. So let us talk a little bit about the parts versus the elements. So because I have brought in this cross section from our section library, all of the parts and elements are automatically created here. I'll go ahead and hide the elements just to explain what we call the part. So the first part is our W shape, and we're just simply utilizing the boundary lines of this cross section, assigning the material to create that first part. Our second part here is going to utilize the boundary lines of the channel, again, assigning that A36 material. Now, if we go ahead and graphically turn off the parts and turn back on our elements, again, these elements are automatically created and they are required when we run a thin-walled analysis. But again, you can see that all of them are listed here in our navigator. Now, this is the information that would be taken into RFEM eventually and allows us to carry out those local buckling checks because we can tell which elements are supported at the edges, both edges versus just one edge. We know the thickness, we know the width of them, but you can see that there are some simplifications made with these elements. For example, we can't take into account the radius here of the channel or the radius here of our web to our flange connection. But if the shape is close enough, then this should be sufficient for calculating the shear, warping, and torsional areas, and the thin-walled analysis would be preferred. But as the cross-section deviates further from the elements, this is where we would want to move to a finite element analysis. Now, if I were to go and run the calculation, I go to calculate, calculate all, I get a warning. And it's telling me that I have several unconnected parts. So this is quite common within our section. And the reason why is because all of these elements here need to connect at their center point. And the issue is going to be this top element here with our channel just sitting on top of the top elements here for our flange. These are technically not connected. So what we need to do is to create what we call a null element. Now, in order to make modifications to this cross section that I brought in, I need to select both of the sections in my navigator here. I can right click and I can choose the option to explode. So now I can make manual modifications to these cross sections. Notice the elements I can now select individually. I'm also going to right click here to ensure that this auto connect lines and elements is turned on. As I draw elements, the program will automatically divide up additional elements that it intersects with. So we're going to begin up here by drawing a new single element. Now, I don't want this element to have any thickness. It's a null element. So we can zero that out because I don't want to affect the cross-section properties. Rather, I'm going to define here the effective thickness for shear transfer. And we could set this to something that's equivalent of the thickness of the weld, for example. So 0.125, we go ahead and input that in. And then what I can do here is to snap to that center point of the flange to the web of the channel here right at the center point, and my null element is generated. I right click once, and I want to do the exact same thing over here on the other side where I snap to the center point and up here to the center of the channel element. I right click a couple times, and now you'll notice here that this element again was broken up where we added that additional null element. The null element can also be seen here in our navigator. Again, it's not adding anything to our cross-section properties. We're just simply connecting those elements with that shear transfer thickness. So now we are ready to run the calculation. If we go to calculate all, we see how quickly that solves. We do not have any warning messages. And ultimately, what we're after here in our table results is the cross-section properties. So area, moment of inertia, again, some of the properties that are specific to the thin-walled analysis calculation, shear, torsion, and warping. So this information is certainly what we need to also bring into RFEM. We would want to save this file with the results by going to File, Save, or Save As. Again, you need the saved results to bring this into the FEA program RFEM. But in addition to the table results for the cross-section properties, you'll notice some additional options to view graphically here. Well, we'll actually give you as well the stresses based on applied unit loads. So for example, I can view the stress based on an applied axial force here to the entire face of this element based on 1 kip. We see 25.5 PSI, or maybe I want to take a look at an applied bending moment here of 1 kip per foot. Again, we can view the relevant stresses. Now, it also might be interesting for us to view the stresses on the cross section for loads other than this standard 1 kip or 1 kip foot. Well, we can also do that directly within our section without bringing it to RFEM necessarily. You'll notice over in our navigator that we have the ability here to right click to create a new load case. And we can create as many load cases as we want. We could even generate a load combination with the relevant load factors. For today's example, I'll just go ahead and give this a single load case name here, load 1, and I click OK. So once we've created this load case, we can apply by right-clicking here on the internal forces and selecting new internal forces. You'll see the relevant forces that we can apply to this cross-section. For example, if we wanted to add in a shear force of -10 kips, we can go ahead and put that in for VZ. If we wanted to apply a bending moment about the strong axes, we could go ahead and put in 100 kip feet. So when we click OK, I can go back to calculate all. All of my cross-section properties, of course, remain unchanged, but now we get this additional option over here in our results shown at the bottom where we can view the normal stresses, or we can view the shear stresses or the von Mises stresses, again, based on that applied shear and bending moment from this load case 1. All right, so that will conclude our first example for today. We now want to move on to our second example. So for this one, I am going to jump over here to my AutoCAD file. I have this relevant cold form steel section shown here. And although the shape is a little bit more complex, you'll notice that the thickness of the wall is identical throughout. So this will certainly be very user-friendly to import into our section because of this. So we will go back to our section here, and we're going to create a new file. We're going to give it a name, example 2, and we want to carry this out again according to the thin-walled analysis. We click OK. And once we have our model, we can additionally go to File, Import to directly import in that DXF file. So I'll go ahead and select the saved DXF file. We'll import into the active model, and now we get some additional options here what we want to do with this DXF file. Again, because this cross-section has a pretty uniform shape for the thickness, we can automatically create both the elements and the parts. So let us go ahead and do this by selecting the second option here to create the elements automatically. We do need to put in the max thickness. So this doesn't need to be the exact thickness, just a number that is anywhere greater than the thickness, because the program is intelligent enough to create the relevant element widths. As far as the part, we do need to assign a new material. So we go into our material database, and instead of selecting from the AISC, we will select here from the AISI standard. We'll go ahead and select this cold form steel material listed first, the A1003-15. We see all the relevant submaterials as well. We'll go ahead and select the first option. So when we click OK, the program will go ahead and import in that DXF file, and we'll see that everything is automatically created for us. So you'll notice here, if we expand the elements and the parts, everything was generated from that DXF file import. So I'll go ahead and hide the elements for now. If we take a look at the single part that was created, again, the program just detects what the boundary lines are here. This part is absolutely needed no matter which analysis type that we're selecting, because it's going to be used to calculate the cross-section properties like area, moment of inertia. But then, because we are carrying out the thin-walled analysis, these additional elements are required. So I'll go ahead and turn off the part, and we'll turn on the elements. And again, you'll notice that this was a pretty easy application, because the program is going to generate all of these elements automatically. Again, this is what's going to be used for local buckling checks once we bring this into RFEM to determine the length to thickness ratio, where these elements are supported at one edge or both edges, as opposed to this one up here that's only supported at one edge. You'll also see that we have the ability here to generate arc elements. So we're not restricted necessarily to just a straight segment, but we can generate these arc elements as well. So really, that's all that's needed for this particular section. If we go to calculate all, you'll notice that once again, we have all of our cross-section properties given to us based on the thin-walled analysis within table format, as well as those unit stresses based on those applied unit loads. We would save these results, and then again, we could bring this over into RFEM. So this cross-section was fairly easy with the DXF import. We'll now move on to our third example. So for the third example, I'll go back to the AutoCAD file here, and this is going to be for an aluminum extrusion. Now we see here it's resembles pretty much a box section, but this certainly has some more complexities up here at the top than our last example. A lot of these elements are going to be different thicknesses. We have notches, we kind of have these openings and grooves. So let us see how we can take this DXF file then into our section to still calculate the cross-section properties. So once again, we will go to File, New to create our third example. Now, this analysis method is going to be set to the finite element analysis. So I mentioned in the PowerPoint that although we would prefer the thin-walled analysis for something like an aluminum extrusion, at some point when the program or when the cross-section gets a little bit more complex, we do need to move to the finite element analysis. So this example will explain a little bit further why we will carry this out. So we click OK. And we're going to go to File, Import in the DXF file once again. We go ahead and select this file from our computer. It's asking if I want to import it into the active model. Yes, we do. But this time I'm not going to create the elements and the parts automatically. Now it is possible, but the elements don't come in so nice because, again, this cross-section is a little bit more complicated. So instead, we'll choose the DXF template for further editing, and I click OK. So now what you'll see here is just simply the line elements from the AutoCAD file itself. Nothing was generated automatically. We see this over here in our navigator as well. Rather, we need to right-click to manually create our part. So we'll go ahead and do so by selecting the boundary lines. We want to create a new material here. So once again, we access the material library, but we're going to choose aluminum and the ADM 2020 from our standard. All of the relevant materials are shown here, but we're going to jump down here to the 6061 T6 for extrusions. Once we have our material selected, we have the ability to select the boundary lines to create that part. Now you'll notice that I will select all boundary lines here with my selection window. The problem is that if I try and click OK, the program's going to give me a warning. It's looking for just one continuously closed loop of lines. And you'll notice that I've included all of the lines at the interior here for the opening. So what I need to do then is to actually deselect these line elements. So I'm going to hold down my Shift key and I'm going to highlight over all the interior lines. And notice they're no longer selected. I click OK through these dialog boxes and I have my part generated. But clearly we need to add an opening to this part. So we can do so by right-clicking here in the navigator to add a new opening, or we have the drop-down feature up here at the top where I can simply select the boundary lines to create that opening. Now, when I do this, the program is intelligent enough to detect this closed loop. So that opening is automatically created here. And now the part is generated. So because we are running this finite element analysis, I can really go to calculate all, and my cross-section properties are done. Remember that the shear, warping, and torsion properties are going to vary. They're going to be a little bit different than the thin-walled analysis now that we are carrying out an FEA. The problem here, though, is that if I want to take this aluminum extrusion into RFEM, I have lost the ability to carry out local buckling checks because I have no elements defined in this model. So therefore, if we do want to consider local buckling, we would want to manually add in the elements to this cross-section as well. So I'll begin by deleting the results here, and I'm going to go back to hiding the part graphically as well as the opening so that we're just seeing our lines brought in from AutoCAD. Now we want to create these elements, and we have some really useful tools down here at the bottom, including this option here to create the elements between parallel lines. So when I choose this option, this allows me to graphically select two parallel lines, and you'll notice that the element is automatically generated. Well, we do so for the sidewalls here, and then we're going to go up to the top to do the same thing in a couple of areas. So we create the element here as well as our vertical element up at the top. Now, clearly we need to clean up these elements. They should all be connecting, remember, at these center nodes. They should be spanning across the full length here of our section. So this is quite easy with that move copy tool once again. Now I'm going to select both of these top center nodes here of my side elements by holding down my control key. So they're currently both highlighted. I'm going to use my move copy tool to utilize this displacement vector again. I'm going to choose the option to click 2 points where I select the center point of this element to the center point of the horizontal element that it eventually should be connecting to. But again, I don't want to move these elements in the Y direction, only the Z direction. So we'll go ahead and zero that out in the Y direction. And now you'll notice that these elements extend up to the center line of our horizontal element. Well, this now gives me the ability to simply grab this node and to drag and drop it, and I can snap directly to that center node point. I'll do the same thing on the right-hand side. And we also need to do the same thing for this small element here. We want to extend it up to the top as well as the center point here. So I'm just going to drag and drop it. The program snaps to that center point, and then up at the top, we want to snap it to where this arc begins. Now there will be a problem here because similar to our first example, notice this element is connected to this one, but we haven't divided this element here. So the program won't detect that these are connected. So what we can do is just to manually connect them with this tool up here at the top to connect lines and elements. And if I highlight over this location here, sure enough, we now get 3 elements at this intersection and everything would be considered fully connected. But you'll notice that for the elements, we have to make these simplifications. So for example, this opening here, we're not really accounting for with this element. But again, the cross-section properties for the finite element analysis are only referring to the part, but we want to create these elements for the local buckling checks once we bring them into RFEM. So inevitably, some simplifications have to be made. I also didn't draw elements up here at the top. Maybe I'm not so concerned with local buckling, but I certainly could draw them in here. And then again, we would want to draw in a null element to connect from this larger element to these smaller ones, like what we did in the first example. Now down at the bottom, we have the same problem here where I want to hold down my control key to select both of those nodes. I use my move copy tool. I graphically select my displacement vector by choosing 2 points. I don't want to move it in the y-axis, as we see here from our axes in the background, only in the vertical z direction. I click OK, and now I have the ability here to grab this node and snap it to the center point, and I'm going to do the same thing on the right-hand side. So now that these elements are created, we can go to calculate all, but keep in mind that really the cross-section properties aren't going to change at all from what we saw before we drew the elements. Because again, these elements have no influence when we're running the finite element analysis. If we are curious, we could go back to the base data dialog box just to toggle to the thin-walled analysis to see what these results look like. And we can go to calculate all. So as we zoom in here, you'll notice that for the properties such as shear, torsional, and warping, we're going to be neglecting some of these areas or simplifying some of these areas of the cross section. So again, as our cross section tends to deviate, or the part tends to deviate from the elements that we can create, then we do need to move to that finite element analysis, but still with the ability to generate the elements for local buckling if we choose to do so. All right, so we'd probably toggle this back to finite element analysis, rerun, save those results to our computer. The next example I actually already have pulled up here. So this one will be just a quick example. We mentioned it in the PowerPoint. We probably have some type of AutoCAD file for this one that we can easily just file, import. You'll notice that the part could be easily created here by selecting the outer boundary lines. Again, we'd want to add openings here for all of the openings, all 5 of them. And we certainly would want to run this particular cross-section according to the finite element analysis. If we toggled this to the thin-walled analysis and we tried to generate those elements everywhere, it would be entirely too complex, that it really just doesn't make sense because, again, our elements are going to deviate away from the original shape. So by carrying out the finite element analysis, we get all of the properties shown in our results, as we can see here in table format, as well as those unit stresses. We also might argue that it really isn't worthwhile inputting in additional elements because local buckling maybe isn't a concern for a cross section such as this one. So that one should be a very easy approach of importing in that DXF file, creating the part, and running the finite element analysis. Okay, so we want to move now to our 5th and final example within our section. For this one, I'm going to go to File, New, and this will be example number 5. We will carry out the finite element analysis because we're going to create a custom reinforced concrete massive section. Now, what's fairly new within our section is that not only do we have the ability to calculate the cross-section properties here, but we can also place the reinforcement in these custom sections. So When we activate the concrete reinforcement, we get a new tab here where we can set the default cover. So we'll go ahead and modify this to 1 inch. When we click OK, similar to our previous examples, we are going to right-click here to create a new section. I'm going to access my section library. Now, we easily could import in one of these massive sections, which is what we'll be doing today. Of course, you can import in an AutoCAD file for massive sections. You can draw your boundary lines up here in our toolbar and create your part manually. So a lot of different options. But for today's example, I am going to select here from the library the massive double T section with chamfered inner corners. So with this cross section, we now have the ability here to just input in the dimensions and the program will automatically update. So we have some nice visualization here to show you exactly which dimensions you're setting. I'll go ahead and modify here the depth to 30 inches. The width will be 45. We have a couple heights to set. That will be 8 inches and 8 inches. And then we're going to modify the chamfer dimensions to 2 inches and 2 inches. And finally, the spacing between those rib elements, we'll set this to 24 inches. So again, the cross section will update automatically based on my input here. If you do jump to this last tab, it's worth noting here that with that finite element analysis, we've added this FE mesh tab here. So you can see that the program automatically sets the FE mesh. It should be adequate, again, to get those adequate results. But if you'd like to refine it, it is possible to add in a mesh refinement factor. Back under the main tab, we need to assign a material to this massive section. So we will visit our material library like we've done several times before, but we're going to choose concrete and we're going to choose the ACI 318-2019 standard to choose 4,000 PSI. Now, if your concrete material is not shown in the library, we can always select one of the existing materials, come in and edit it, and select a user-defined material here to modify the compressive strength or any of the material properties. For today, we will just go ahead and utilize the 4,000 PSI. So once we have set the material, the cross-section is brought in here into graphical view. Now, it is possible as well if we right click to explode the section, we can add in additional openings such as a rectangle or a circle. If we did, again, want to account for that with the cross section property calculation. We'll go ahead and leave this without openings for today. Now, the first step with our reinforcement is to define the stirrups. And because I've activated that under the base data, I have a couple different options here for my reinforcement. We're going to begin by right-clicking on stirrups to create a new definition. We do need to set the material of the reinforcement steel. So we'll visit our library here. The program automatically sets this to reinforcing steel according to the ACI where we choose grade 60. The stirrup diameter is input here in inches. We'll choose a number 3 bar at 0.375 inches. The stirrup diameter of curvature is also input. We can see this visualization picture over here on the right to see exactly what curvature we're setting. We'll go ahead and leave this as 1.5 inches. And then we want to set the cover points. So the program has automatically created some helpful points here that we can easily snap to. So for our first stirrup, what I'm going to do is to select these 4 corner points here, but then I need to click a 5th time in order to close that loop. So when I click OK and I hit apply and next, I still remain within this dialog box, but you will notice here that that first stirrup was generated. All of my information was remembered from my previous input where I can now put in my second stirrup and I click again on these 4 vertical points here, but then I click a 5th time to close the loop. I click OK, I hit apply and next, and we see that stirrup generated here in the background. And we're going to do so one more time over on the right side by clicking on the 4 points. And my 5th click will be to close the loop. And I click OK, I click OK. So now these stirrups are generated. We can select them here. We can edit them easily within our navigator. It's now time to define our longitudinal reinforcement. So right below the stirrup input, we can right click here to create a new bar. So within this dialog box, you'll notice that we have several different definition types. So we'll move through these and they'll make a little bit more sense with our example model today. We also have the ability to define reinforcement layers. And you might be wondering, why wouldn't we just put everything in one layer? Well, when we bring this into RFEM, if we have defined different layers for our different reinforcement input, then we have the ability to modify the lengths differently for each layer. And we'll do this in our example today. So therefore, I want to create some additional layers. So we'll rename the first layer to top. We'll go ahead and make a copy. Our second layer will be bottom. Make a copy again. This will be bottom additional. And finally, we have our fourth layer, which is going to be sides. So when I create these layers, I can now select them here within my dropdown. We'll begin first with the top layer. My definition type is going to be a single rebar defined by a point. I do want to modify the bar diameter. I want to select number 5, so we would input in here a dimension of 0.625 for the diameters in inches. And then I can graphically select the point that I would like to place this longitudinal bar. So we select our point in the upper left corner here. I hit apply and next. We should see that inserted within the background. I'm going to do the same thing down here at the bottom. Apply and next. We're going to do it over on the right hand side at these two locations. Apply and next, and then my fourth click here will be at the bottom right. And now I click OK. So we see those 4 bars inserted here at the top of our section, and they're also listed over here in our navigator. We're going to right click to create a new bar definition again, still part of the top reinforcement. This time though, we want to select the option here for multi-uniform. The program still remembers my previous bar diameter input. I want a total number of 2 bars, and then I select the 2 points that these bars should span between. So what I'm going to do here is to select my point inside my vertical stirrup, and I can also see a nice preview here shown within this dialog box. I click OK, and now those 2 rebars are shown. Now, instead of the apply and next option, we also have the ability here to work within the table. So if I jump to the bars tab, here's all my input for my longitudinal reinforcement, where I can take this last input, I can right click, I can copy the row. So all of the information I input for these 2 bars up here are copied. And then I can just graphically select my 2 points where this should be located for that copy. So I select the vertical reinforcement over on the right, and then that's simply what's needed. So it's up to you and your preference of how you would like to input in that reinforcement. We are going to create our final reinforcement for that top layer. We'll go here once again to the reinforcement layer type 1 top. The definition type is going to be multivariable this time. Same bar diameter, but we want to increase this to a total of 5 bars. And I'm going to graphically select, again, my 2 points that these bars should span between. So we choose the point on the left here and the point on the right. And once we've input in these, we need to specify how the spacing will vary along this length. So the spacing from my first point to my first bar is actually, and actually I'm going to decrease this by 1. I want a total number of 4 bars here. I'm going to set this distance to 1.5 inches. My second input is going to be 5.75 inches, and then the program's intelligent enough to recognize that the last dimension should be 1.5 because we know the total length between these 2 points. So once we have input in this information, again, we see the visibility here of what this will look like. We click OK, and it's applied to our cross section. Moving on to the bottom reinforcement, I am going to right click to create this new definition type, but this time we want to toggle to a different layer bottom. This one is going to be multi-uniform. So we want uniform spacing for these bars. We want a total number of 2 bars. And as far as my points, I'm going to graphically select these down here at the bottom. And I'm going to hit apply and next because rather than the table option, I can easily select here just the next 2 points on the right hand side. I click OK, and now we see that bottom additional reinforcement. Moving on to the bottom additional reinforcement, we create a new definition type, but now we toggle to layer number 3. So with layer number 3, we want to keep this as multi-uniform as well. We want to increase this to a total of 3 bars. And I'm going to select my points here, the bottom left. So my first point is over here on the left. My second click is going to be my point on the right that I would like these 3 bars to span. But you can see that we have a bit of a conflict here where these bars are now overlapping. So this is why we also give you the ability here to set a vertical offset. So I can go ahead and input in 1 inch, and now we see those bars move in the upward direction so that we don't have any overlap to our bottom bars. So I'm going to hit apply and next, and I'm going to do this exact same thing over on the right hand side by clicking my 2 points here. Everything's remembered from my previous input, so we can see here the additional bottom reinforcement. We're finally ready to input in the last reinforcement. This is going to be for our side layer. So for the last time, we go here to a new bar, and we're going to choose the layer type for sides. This one is going to be multivariable because I do want the spacing to vary. We want a total number of 5 bars here, and I am going to decrease the diameter. Maybe we want to use something smaller for the side reinforcement like number 3s. So we'll just use 0.375. Then I also want to zero out the offset. So the program remembers that from my input last time. We'll go ahead and zero that out. And then I graphically select the 2 points here along the side. So we're going to click once up here at the top and once down here at the bottom. And then I want to input in the specific spacing between these bars. So remember, this first input is going to be from this first point to the center of my first bar, and that's going to be 0. The additional spacing here is going to be between the interior bars. So this will be uniform spacing of 5.75. And then again, the program is intelligent enough to detect this final dimension. We get a nice preview here shown in our dialog box. If we hit apply and next, I can graphically select the points on the right hand side. I hit apply and next. I'm going to do this again over on the right hand stirrup in both the vertical directions, apply and next, and then I'm going to go ahead and do this one last time. Okay, so once we click OK, we now see all of our reinforcement drawn in this section. So this is taking advantage again of those different layer options, the different longitudinal bar input options. And now we can finally go to calculate all. So the cross-section properties, just like our previous examples, are available to us. Keep in mind that the reinforcement is not influencing these cross-section properties. Rather, we're going to use the reinforcement once we go into RFEM for the concrete member design. But we would want to save these results to our computer, and we're now ready to finally go into RFEM to integrate these cross sections into bigger member models or full structure models. So I will go ahead and jump to RFEM here, where for the sake of time, I have already drawn a couple beams that we will cover, but Again, for those of you that have not been in RFEM before, like I said, the interface is almost identical to our section. We have the navigator to work with over on the left with all of our input data. We have our tools up here at the top, or we can work with our table. So what you'll notice is I did create a couple beam members here utilizing our R section files. And we'll begin with, if I render this to a solid view, you can see our custom reinforced concrete section that we just defined. So what's nice is you see the rendered shape for this cross section. And if I turn this into a transparent view, we also see all of the reinforcement that we have applied to this cross section. So this member is 30 feet long. We've applied a couple support conditions to the ends, but if we double click on this member, you will recall the 4 different layers. Well, here they are under the longitudinal reinforcement tab, where I can go ahead and cycle through each one of these, and you'll notice they're highlighted graphically. But this now allows me to modify the length for the different layer types. So for example, we have our additional bottom reinforcement. We can see a nice preview here as well over on the right-hand side. If I didn't want this to span the full length of the member, we can modify this to something like 20% to 80%. I click apply, and now we should see that that reinforcement here was shortened to just the interior of the beam. So again, this is the benefit of utilizing those different layer options. We'll also see here that I did want to mention is how do we pull in this cross section? So this can actually be done within a new RFEM model. We can right click to create a new section, or as we draw a member, we can do so. But you'll notice here that for my massive section that was brought in, we accessed the cross-section library that again looks very similar to our section, but this time we can import in from the R section program directly. So if I were to click on this, this takes me to the Dlubal Center, where I would want to right click here to maybe connect a folder as a project under the existing project folder. And then here are all of my example files for today. So when we bring in any one of these cross sections here, what you'll notice is that the material is automatically considered. That FE mesh that we talked about is also brought in. So this is the big benefit here of creating those custom cross sections and integrating from our section into RFEM. If we jump down to the aluminum extrusion, which I'll go ahead and cancel out of here to show this member, again, we get a nice rendered section here, and I'll go ahead and turn off the types for nodes so we can see this cross section in more detail. But this is also a unique benefit of our programs, is that you will see the rendered section just like what we had in the AutoCAD file. So this is nice in knowing how to orient the member, strong versus weak axis. Going back to the sections here, and I want to pull up this particular cross section that again was brought in from the cross section library directly from our section. You can see the material again was also brought in, but we can modify that here by visiting our material library. But important for these sections that we have added elements. So remember, this was carried out according to a finite element analysis, but because we took that additional step to apply the elements here, now you're going to see each one of those listed within RFEM. And we tell you exactly how these elements are supported, either one side or both sides. We know the width, we know the thickness, and this will be eventually used in the ADM model. Okay, so now that we have imported in these couple members here, we would want to apply loads. So go ahead and turn off the reinforcement here for our member. I created just a couple simple load cases for today. Dead load with an applied member load, and we also have a live load. When we combine these into the load combinations, you can see here that they will both be applied to the member based on ASCE 7 or NBC, however we're generating those load combinations. Now, RFEM is the program responsible for the full analysis. So once we bring this cross section into RFEM, we can apply the loads and to get information like deformations, support reactions, the internal forces. Again, this is all included in the base program, RFEM. But if we wanted to take it a step further and to actually design these members, so for example, design our aluminum member according to the ADM or our concrete member according to the ACI or the CSA standard, we would need to activate these add-ons. So we go to the base data here. And under the second tab are the relevant add-ons that we have purchased with our RFEM license. So by activating here the concrete and aluminum design, we're not only going to carry out the analysis, but we'll further carry out the design for these two material types. And under the third tab is where we can set the relevant standards. So for example, concrete design, we can select the ACI 318 or the CSA standard. Aluminum design, we can select here the ADM. We can generate our load combinations automatically according to the ASCE 7 or the NBC. So once we've activated these add-ons, we would input in the relevant limit state types within table format for these add-ons. We would tell the program which objects to design. And ultimately, we can run the calculation. So if I go to calculate all, the program will go ahead and run through the load cases and the load combinations according to a second order analysis. But then you'll see that we will take advantage of those add-ons to further design the members. So once we're done with this calculation, we'll see over here in our navigator, very similar to our section under our results tab here, we can view these static analysis results. So again, with the static analysis that comes from the base program RFEM, we can view the global deformations. I can turn this into a wireframe view. We can view the member internal forces like axial forces, shear, or maybe bending moments. If we want to view just the aluminum member here, we can create a visibility so that bending moment diagram is a little bit bigger. So again, this is the analysis portion, but then we want to toggle down to the concrete design. So you can see here the table also updates to the concrete design add-on, and essentially what we're doing here is designing this concrete member according to the ACI standard. Now, at the current time for members or cross sections that are brought in from our section, we will only carry out the single strength design check for axial strength or combined flexural and axial strength. So we are working on additional checks for these custom cross sections, considering the custom reinforced layout like shear or perhaps moving to serviceability. We'll recalculate deflections based on the modified stiffness of the cross section as well. But for now, this is the only strength design check available. We also can carry out the serviceability crack control checks. But if we jump to the design check ratio here for this particular cross section, you will notice that if I zoom in here into the design check details, I see all of the relevant formulas, equations from the ACI, and ultimately the design ratio. We also can activate here the interaction diagram. This interaction diagram is going to show us in 3 dimensions here, the interaction in terms of the table format as well, exactly where we're at for this particular custom cross section. If we're interested, we can also access the stresses on the diagram. So this cross section, as you can see here, will go ahead and bring in the reinforcement from our section where we can see the stresses on this custom reinforcement layout as well. Again, this is based on the applied loads at this particular X location for this design check. Now, graphically, we can view additional information. So for example, we're currently viewing the design check ratio, but what we'd like to activate here is maybe the required reinforcement along the length of the member at the bottom, just based from the analysis only from those applied member loads. Well, we can overlay on top of this the provided reinforcement at the bottom. And remember, we shortened that additional reinforcement to the center of the beam only, so that's why we see a jump here. But ultimately, the provided reinforcement should be greater than the required reinforcement. Sure enough, it is, so everything seems to check out for this particular member and this design check. Now, very similar is we can toggle here to the aluminum design. So we're jumping now to the ADM standard. Unlike concrete, for anything for hot rolled steel, cold formed steel, aluminum, we will carry out all design checks for these custom sections. So there are no limitations with this. We do design them according to general members. So therefore, the results here for our ADM will show us all of the various design checks. So for example, I have lateral torsional buckling, where we actually show you the buckling mode shape based on an eigenvalue analysis. But what I emphasized many times before is you will see here the local buckling check for this custom extrusion. And we go here into the design check details. And yet again, I'll scroll in here so that you can see the formulas from the ADM, the design ratio. But if we expand the table over here, we can see each one of these elements that we defined back in our section. We see how it's supported either at both edges or one edge. If it's in compression, we'll classify it according to chapter B. So again, the really powerful thing that the program will do for ADM, AISI, the CSA standards with those local buckling checks. Again, we can also access here our cross-section profile to view the stresses, such as the von Mises stresses under the applied load for this custom section. Okay, so we will jump back to the PowerPoint for today to conclude our presentation. As always, I know this is quite a bit of information, but this presentation was recorded. It will be placed on our webpage where you registered for the webinar, usually within a day. All of the models that I used in today's examples are already uploaded to that webpage, so you can feel free to download them. If you're not already a customer, you can also access the free 90-day trial version of both RFEM and our section. So it's full capability. It includes all add-ons for the full 90 days. If you have any questions about today's presentation or any of our products, feel free to contact our Philadelphia office with the information shown here at the bottom of the screen. So our phone number is 267-702-2815, and our email is info-us@dlubal.com. If you are interested in learning more about RFEM or possibly a more in-depth online demo and you'd like to talk to our sales team, feel free to contact us either with this QR code that's available in your PDF handout in the GoToWebinar, or of course you can reach our Philadelphia office again with the information shown here at the bottom of our screen. We will have many more upcoming webinars. These will occur approximately once a month. You can register at dlubal.com under support and learning webinars. As most of you know, I will send out a couple reminder emails before these take place, so you can keep an eye out for that next month. PDH certificates will automatically be emailed to all participants. So this isn't automatic right after the webinar ends. It does usually take either a day or two. It will be emailed to participants who are here for the full 60-minute duration. This is a requirement of the states that we are pre-approved providers, that you are here for the entire duration of the webinar in order to receive that PDH. Now, if you watched with a colleague or you watched in a conference type setting and you yourself did not register for this GoToWebinar, but you were here for the full duration and are wanting PDH, you will need to request that by sending us an email at info-us@dlubal.com. So again, if you yourself did not register, you were here for the full presentation, go ahead and send us an email, let us know who you watched it with, and we will be happy to generate that PDH certificate for you. And with that said, I want to thank everyone for attending, and as always, we hope to see you at our next presentation. Thank you.